And we are live.
Hey everyone, welcome to another Wolfram Institute Live Science stream. We're trying a new format this week, so please entertain this new experiment on our part. So today we're going to hold a roundtable with all the fellows, and we're going to discuss research that has been done this week and last week. So in the past, you've seen us host streams that that take a single project as its focus. And I thought, given that and I think many of us have enjoyed the community fora perhaps the most because it's been more conversational, it's been more informal, it's involved all of us. I thought it would be better to have a format where we can kind of share things that we've done that we found exciting, or share challenges that we've encountered, and we could kind of chat about it. I thought that would be a better way. It's an experiment in trying to do open science this way, so that people feel less that they're basically just watching meetings that we're holding, and more that it's a kind of a more conversational, collegial kind of format in which we can discuss the work that we're doing. So if there are, I don't know, if anyone wants to begin and chat about things that they've been doing, that would be nice. I mean, hopefully we don't have to like pick on each other or call each other out.
Yeah, I'd rather go not first because I'm wrestling with the whiteboard thing. Um,
Yeah, sure.
I'll be ready to share something.
Well, I can show my hypergraphs again.
Yeah, I was gonna say that actually Nick probably has a chunk of
Yeah, okay.
my stuff as well.
Okay.
Okay, hold on.
This will actually be useful for me as well to see recent stuff.
Yes, some updates to this interactive drawing tool for the hypergraphs.
Okay.
Uh, well, the first thing that changed since last time, I guess, I've added this additional rendering for this null edges or naked edges, right? Like this thing you see there is just a edge without vertices, which is not usually a part of a definition of the hypergraph as it usually is defined in the literature, because they usually have this definition that the hypergraph contains edges which are subsets, but not empty sets, not empty subsets of the vertices. But our hypergraph is more general than that. I personally don't see a reason why we shouldn't include such edges, right?
So Nick,
also
just to call back to one of our earlier conversations, that's basically an implementation of scalars, right?
yeah, they should be represented as scalars if you make a proper tensor representation or hypermatrix representation of the hypergraph. Those empty edges are gonna be like counting and be representing as a scalar. So if you have
So are you guys going to use this for some sort of spectral theory?
I mean, it's just representational at this point, but could be useful to
No,
have.
just because you mentioned scalars, I was wondering if it was relevant.
right now you can just see that right, if you take this hypergraph and you make a hypermatrix out of it, I think it will not like in the input form. It's just a list of tensors or arrays in our case, and the first one represents a scalar because we have a single null edge there. There is one in there. So this first tensor, which is zero rank tensor, is a scalar, and that would encode all the null edges in the hypergraph.
So what if you had like five
It's gonna be just
empty
five.
edges?
It's gonna be five. So like if you add them, and they're add it on top of each other. Now there's like.
I think it'll be nice to just as cosmetic. It'll be nice that if they stack, they add some kind of count.
What do you mean count?
Like the integer value. Because, I mean, it's just cosmetic, I guess, because, I mean, stacking at the moment doesn't really do anything. So you could either have like several nested circles or some kind of visual cue of, I mean, that's not very practical because, you know, you go above 5 or 6 and it's already like a big mess in the screen.
Oh yeah.
But
Well, I don't know.
yeah, I mean,
Those are really kind of stacked. They're not shown to each other. They just because they're not attached to a vertex, right? They're just they can't be put randomly on the screen. It's like there's no particular point to attach them to,
I know,
right?
I know.
So I can scatter them around when I create one. Right now they're even kind of represented very hackily with the special vertex because there's no way to encode it as an edge with the coordinate, right?
Sure.
Because I also as a graph, I also encode all the embedding and coordinates of the vertices separately. And in order to encode where this new edge is located, I have to like hack it around to present this special kind of vertex.
What's the motivation for including them in the first place? Like, they're not usually included. You're suggesting that it would be good to include them, but what might you do with them? How might they be used?
Well, they are more general representation. If you think about other representation of hypergraphs, especially as this graded product of like this hypercube tensors, right? There's no reason to not include a 0, 1,
Yeah.
0 rank one, right? And that would be more natural to include them rather than just say, okay, we don't allow that for some reason.
Yeah, I mean, one way to explain it is that if you, I mean, remember how hypermatrices or hypergraphs are essentially dual to each other. So when you look at the hypermatrix side, I mean, it's just natural to take one single scalar as some kind of zeroth order hypermatrix, and that's what this corresponds to.
Yeah.
So it's purely like a convenience thing. It's not very deep.
Okay.
Yeah, so it's a hypergraph is not just extension of edges to the higher order; it's also an extension to the lower.
Lower, yeah, that's
yeah. We had like unary edges like that, right?
Yeah.
Which is just kind of stuck on a single vertex. Well,
didn't that just create? What you just created like a quaternary edge, right?
Yeah, this one is a quaternary one.
Yeah.
You have to put it multiple times like that. This is multiple unary edges.
Yes.
That's the difference.
Can we generalize this to negative order?
Well, if you have an idea for that, then yeah. But I haven't heard of tensors with negative.
Maybe some dual construction, I don't know.
Negative dimension.
Well, you can just weight them over integers. Over integers.
But if you think of those as a dimension of a tensor, that would be a negative one would be some negative dimension vector space or something. And that I have an interpretation of.
No, there's no very clean interpretation of negative dimension, but I think there's a fairly clean interpretation of negative order edges. You're basically just weighting over integers instead of weighting over naturals, because everything is weighted effectively because these are multi graphs, right? Multi hypergraphs. You can just weight over integers, and effectively, you have the zeroth order, and then you can arbitrarily say that positive weighted edges are of the corresponding positive order, and negative weighted edges are of the corresponding negative order. Right. So
we actually have a different idea. It's like usually you can also put negative sign on the covariant indices. So all the contravariant you can treat as positive, and all the covariant treat as negative.
With a construction like that.
Yeah.
What is that?
It's like, for example, if you take a random tensor or an array, like take a random real 0 to 1 and 2, 3, 4, right? This is a tensor with 2, 3, 4 dimensions, right? And it's treated like all of those three indices with 2, 3, and 4 dimensions. You treat it as a contravariant one, right? But if you treat one of them as a covariant instead, you can write it as like that, right? And it is just an identification of, okay, this first axis is also two-dimensional, but you treat it as a covariant one and it goes into other direction. If you also represent them or render them diagrammatically, you can also, when each index is like an edge or an arrow that goes from a tensor that represented by a box, you can just represent an arrow that goes into a tensor, so like an input. That would be a negative one, and the one that goes out from the tensor box would be a contravariant index, and this is like an output arrow. So you can treat them like that.
Sure.
That's kind of more natural representation.
Yeah, but I guess the arithmetic of the indices only really works out in aggregate, right? Like if you have this many covariant indices, this many contravariant indices, like you can effectively contract them, which amounts to arithmetically adding these numbers, right?
No, this is like, there's no much of arithmetic of those contractions. If you want, usually contract indices that are separate, like a negative and a positive. Covariant contracts with the contravariant. So in a sense, you kind of only allowed to contract things of opposite sides.
No, but that's what I mean. That's what I mean.
Yeah.
That's what I mean by the arithmetic. That if you take a order 1 positive 1 tensor and order negative 1 tensor, the contraction is the arithmetical sum of those two values, right?
No, they're not summed together. I
No,
don't
but-
see what
No,
is
no,
being
but
summed.
wait. No. What I'm trying to say is that when you contract an covariant 1 with contravariant 1 tensor, you get an order 0 tensor, a scalar, right? So what I'm trying to say is that I'm actually asking about this. I never saw
Oh, yeah,
this
maybe
this
kinda,
negative
yeah.
positive representation, but like there is clearly this correspondence between the fact that you are contracting and the fact that you can arithmetically sum. But what I'm saying is that obviously that's kind of an aggregate arithmetic because I mean you contract indices in pairwise manner. You don't just put them all in a bunch and contract them all in a bunch, right? So I'm wondering.
Yeah.
I mean, I see the point. You can. I mean, negative is just like a notch. That it's like a binary notch. Sure, you can indicate something with a sign, but I wonder whether the arithmetic pays off in any way beyond that sort of.
Oh, that's cool. That's cool. I never thought about it as arithmetic, just adding indices together. Then it makes also sense to add different dimensional, to contract different dimensional indices too, right?
What do you mean?
In a way, it's like what would be if you just have a vector, a three-dimensional vector and another three-dimensional vector.
Hmm.
If you add them together, you have to have a six-dimensional one, right? So it's like it's just a concatenation, like, right? So we
What do you mean if you take the direct sum of their spaces or something? Because you can add them in 3 dimensions, right?
well, if you're adding the actual dimensions, so that this interpretation, if you only contract negative and the positive one, and you get zero-dimensional thing, which is scalar.
I think we are no. I think we are confusing two concepts because we're confusing tensor order and vector space dimension. Because
No, tensor order is just the length of this list of dimensions, and each particular
Sure.
integer is a
yeah,
dimension.
of course.
That's what I mean. It's like when you
Wait. Okay. Wait. I see. Yeah, well, I mean, it still makes sense because, I mean, the arithmetic has to work out because you can only contract indices of the same dimension anyway. Right?
Yeah, but but I also think, what would be the natural extension of that? Of the notion of contraction when you just, okay, the operation of contraction adds the dimensions. Just the definition, when you treat the covariant as a negative dimensions thing and the contravariant as a positive dimension, and the contraction just adds them together. What would be the natural operation for that when they're not just opposite signs of the same integer, like 2 and minus 2 to get 0 scalar when you just sum things over? if you have 3-dimensional vector and a 3-dimensional vector, you should produce a 6-dimensional one. So it's something like a concatenation things.
Sure. Yeah.
So,
Yeah, I never thought of assigning signature to dimensions.
We only actually have an hour to go through.
Yeah. Go on.
This is interesting. Take a note of that. But so okay, Nick? What else do we have to look at on the hypergraph side besides the addition of these empty hyperedges?
oh, I can show the rules again because I think covers at least haven't seen those.
Yeah.
Right, so that you can have the hypergraph rewriting rules like that. Just input and hypergraphs form a rule, and there can be general hypergraphs with those null edges and naked vertices floating around, and they also have their interpretation. It's very interesting when you have, like for example, you can actually just act with this rule on a hypergraph, and you get this list of associations with a bunch of information on what actually happened. I think I've even included more information since this example. Now I have also deleted vertices, and this map, which kind of makes things a bit more clear.
So you pass the hypergraph rule function. You pass two arguments, which are the input and output.
Yeah, this is the input hypergraph, output hypergraph.
And does it check? Does it check for like some context that is preserved, like some of the vertices being the same or something?
Sure, yeah. They basically, first you look for the left-hand side of this rule in your input hypergraph, right? Some of the match vertices would be the vertices that matched, and this is the map between those. It's like, what would be, I think, the vertex on the left-hand side, what would be, it corresponds to the vertex on the input hypergraph, like on this one, right? This is like a very direct map, like here. Here's a direct map, here it's a little more trickier, because this one is matched, because I'm asking to find the match of a single edge like that and this ternary edge.
Yeah.
And if you input this one, I can even match this or this one or this one, right? I have two options to match my edge against. And in the second case, this 2 and 3 are kind of overlapping each other. They get mapped to the same vertex. See, it's like this 2 is mapped to vertex 3, and the 3 map also mapped to the vertex 3. Like this 2 mapped to this 3, and this 3 is mapped to the same 3, vertex number 3. Okay.
Wait, but
So
why I'm a bit confused. Why do we have why do we have vertex maps as a
Well, because you kind of treat vertices on your left-hand side of the rule as some kind of patterns, right?
Sure.
They're variables. You're not looking for the vertices verbatim, like not just like I could have renamed these vertices to A, B,
Yeah,
C,
yeah.
D.
Oh, I see. Okay, so it's not. So it's a coincidence that they are the same names as in the
Yeah.
the thing that. Okay,
Right.
yeah. I see. Yeah.
So-
Makes sense.
So you treat those vertices on the left-hand side of the rule as patterns. They should be binded to
Of course,
some vertices
Of course. Yeah.
on your input hypergraph, and this is the binding map, essentially. And in the second match, one of the vertices, two vertices of the rule match to the same one. So there's two situations that can happen. We can inspect this a little bit more. I
Is
think I
that
have highlighted this.
Yeah.
This is like a function that highlights what actually get mapped. Maybe it's a bit more clear. Again, these two situations. Here I mapped the matched edges are this one, and this is the output hypergraph.
Yeah, but it's not
The
clear to
dashed
me.
one is the
Yeah,
output one.
that looks great, but it's not clear to me that if you specify that the rule as it's shown on the screen, right at the top, there is 1, 2, 3, 4, 5, and it's 1, 2, one binary edge, 3, 4, 5 ternary edge. I mean, it seems to me that the topology has to be that 2 is distinct to 3, right?
No, I don't think that's how it's treated in the, I guess, at least in the Woofer model case. But but here it's even more powerful than that. Because here the hypergraph, it can also handle when this naked edges, naked vertices. I can add on the left-hand side a vertex without any edge. And it also can match arbitrary vertex on your input hypergraph. And it can be removed from
Actually, now that I think about it, that makes sense, because these are, after all, these are hypergraphs. These are not necessarily labeled hypergraphs, right? So I think this should be fine. Yeah, exactly. Okay, sorry, yes, that makes sense. Apologies. Yeah. Makes perfect sense.
So the labels on the rule are completely arbitrary. You can assume that they're variables, like x blank, y blank, z blank, that you bind to some other vertex on your input hypergraph.
So I guess then the rule is strongly tied to the edges, right? It's like a edge. It's more like a. I mean, this is what we discussed before. It makes sense, right? Like it's more of a edge rewriting rule, not so much a hypergraph rewriting rule.
That was how it was treated before, but they also add this new rule treatment when you have these naked vertices.
Sure.
Because if you have a hypergraph, vertices also take part in the rewriting rule. You have to bind this vertex without any edges to some other vertex on your input hypergraph, and this vertex also can change the output. It can be completely removed, because if you only match edges, you're not. If this vertex also participates in the other edge that is not part of the matching, it's not going to be removed. But if it is like vertex which is not part of the, basically you can remove the vertex completely. It can even change the hypergraph outside of the matching edges somehow. So it's a little bit more powerful.
Right.
We can try some example of that.
And maybe we should.
Or maybe.
Yeah, talk about it tomorrow. Yeah. Give way to Łukasz or Richard.
Well, Carlos, you're kind of the natural successor to Nick presentation-wise, since you guys are working on the same project. Do you mind going next?
I have to get this loading, unfortunately. If someone can go first, because I keep restarting the tablet I have here and trying to get it work. Because I'm gonna join with the tablet. Hopefully, I'll get it. Otherwise, I'll just take a picture.
I can show our red rectangles.
I mean, it's not that I have like a massive thing to show. It's just that I had some notes to explain something I'm thinking about.
Yeah, that's fine. Okay, so we're gonna take a detour from hypergraph land, and we're gonna look at Eisenstein series and Hecke operators. They're completely different. That's okay. Well, I don't mind bouncing around. Hopefully, viewers don't mind bouncing around too.
Yeah, so we basically focus on producing nice examples and visual for our report and stuff. So yeah, you have this thing called Eisenstein series. How do you explain what are Eisenstein series?
Start from opening that resource function doc page.
I don't think that's probably the best way to theoretically explain it to people.
I can show the formula later, but later actually computed it straight from the init sum. But okay, so these are these functions that are either in Q representation inside the unit circle, or you can also unwrap it. Let's call it that, to upper half plane. So this leaf, this little leaf here, is the same as here on 0, and actually here at -1 and 1, and this one is the same was here at half, and
So okay, Eisenstein
also,
series appear in the study of modular forms and
yeah,
then automorphic forms, and in particular, there are these things called eigenforms. So what's interesting about eigenforms in this branch of math called, I guess
yeah,
we could
Eisenstein series form
call
form a
it,
part of basis for modular
uh-huh,
forms.
yeah.
And we also have cusp forms as the other part, and yeah, these are Eisenstein series. The difference is basically that cusp forms are zero at the infinity. In this representation, infinity is actually in the middle, like in the center of the circle. Here. That's what this complex infinity gets mapped.
So
Okay.
the idea of an eigenform is there are these things called Hecke operators that Lukáš will explain. And basically, if you have some form and it's an eigenvector for all Hecke operators, meaning it only changes by a scalar, then the thing called an eigenform. So an Eisenstein series is the only example of a non-cuspidal eigenform, and there are also cusp forms and new forms. But so we thought we would do some experiments that actually test this property. So we would apply some Hecke operators to the Eisenstein series and see if we could get the eigenvalue.
Yeah, it's called cusps because when you actually look at the quotient of upper half plane by your modular group, yeah, by SL to Z, you get this 1 point, which is like this, and like basically every rational number and infinity is such a cusp. But
not in the Eisenstein case, though.
no, like you have the cusp, but it's not zero at the cusp. Right?
Yeah, yeah, okay.
It's
Yeah, right.
something,
Right.
some real number here. I don't know exactly. But, yeah, so what are those? Here, I just checked how mapping works. Okay, yeah, and you have a lot of stuff here. You have a lot of formulas for this Eisenstein series. So I use this one here, and it does not want to converge that well. See, like
No,
this stuff, but yeah.
But this one looks right. Yeah.
This one looks right. This one is pretty close to the actual series, and if you, which one is that? The second one. So you unwrap this to upper half plane, it looks like this, like the left half of this, because the.
But this one's not. We don't. This is an outtake. This plot though.
Yeah, but
correct, right?
if you only look at the like left part with like negative real part, then it looks right, and it just repeats. And just copy paste it. Okay, and what is this? What is this? Yeah, some transformation, whatever. Basically, what is the most exciting about this are these red rectangles?
Yeah.
Because
you have to explain why. Yeah.
There's this thing. Okay, so here we have formula for Eisenstein series of given weight and complex number, complex argument. It's like that. I computed only 2000. It's supposed to go up to infinity. Whatever. Yeah. And we have a Hecke operator. Hecke operator is something that you apply to Eisenstein series or any other function, but Eisenstein series are supposed to be like eigenfunctions for all Hecke operators. Hecke operators are indexed by prime number and also act on Eisenstein series with a given weight. Here I just hard-coded that it works like Hecke is actually my Hecke is actually Hecke acting on Eisenstein series. And the formula is just like that. This is Hecke operator. It comes from summing over different cosets in your group if you mod out your group and look at the stuff. But basically, you have many of them. It should be p plus one of those if p is prime number. You can have Hecke operators which is not indexed by prime number also, but we can implement it. But yeah,
Okay, so
this is like a nice little formula.
so what did we
Yeah.
find?
Yeah, so there is Hecke for weight 4 corresponding to number
Prime
2.
2.
Yeah, and I divide Eisenstein acted with Hecke operator by Eisenstein, and yay, it's a constant. It's a real constant. So yeah.
So this is okay. So just we're
Yeah,
going very quickly.
that-
The point is if you take the corresponding Heck operator for okay, prime 2 for Eisenstein series of weight 4, then you divide by the Eisenstein series of weight 4, you should just get some scalar. It should be your eigenvalue. And so that's why the plot is just completely red. Łukasz and I were like screaming in joy to find this. It was like a football match or something. And then after some torture, we eventually got an actual table of these.
Yeah, here you see separately Eisenstein, and Eisenstein acted with Hecke operator, and you can like visually see that it's the same modulus on positive number because color didn't change. Right. And
Have you tried to sum it numerically until convergence?
I'm
Have you
summing
tried
it.
to sum it to infinity until, but it would do it actually until convergence?
Like here, or where?
Yeah, you replace it with infinity and sum and make sum to n sum.
Okay, let's try that.
Right? It can, in some cases it would be even less than 1,000 sum elements will be summed, I guess. Right? Yeah.
Okay, and okay, so let's maybe try.
That's the table, by the way, for people who are
Let's
wondering.
maybe try with this. Okay, and
But we've never had
introduce
any
the table.
success with the street plot.
Yeah, we produce the table. Basically, so what is that?
These are eigenvalues for
Here are different weights.
different primes and different weights for the Eisenstein series.
Different weights and
Yeah.
different primes. Okay, so you have weights
It
from.
diverges, right? So it's supposed to be diverging, or it's an artifact of you summing over up to the 1,000. Because, well, the numbers are so big.
No, the numbers are just huge numbers.
Supposed to be like that.
This is an eigenvalue. Yeah.
We actually, I mean, Łukasz, in all modesty, we actually don't know what the eigenvalues should look like.
Yeah, we can check. But it looks
We
alright.
really have no.
It's
we
the
don't
same if
actually
you
know.
sample at different points, right? Because I just take a Hecke and divide it by Eisenstein, and I just take one particular
Yeah, because
number.
the whole square,
evaluate
is the same uniform color. Yeah, right.
And it's actually consistent. So I think that's the right way to numerically calculate the eigenvalue. But okay, and now we wanted to plot it, but something didn't work, so let's try with this n. So we don't need n anymore.
I can imagine if we had like a live stream where we we were just running something and we just sat quietly for half an hour and let the thing run.
Yeah, so as it computes, like let me. Where are the plots?
Oh, actually, by the way, can we
Yeah.
while we ask Nick, since Nick is here, this Jacobi theta function.
Oh yeah.
Yeah.
So
Like,
here is the plot of elliptic theta,
Okay.
the complex plot, and it's like consistently this result, and then I felt like it doesn't work at all. But you can
well, you're running something
you
already, so you won't be able to run another thing. But you could show your you have an example there below.
yeah.
You have the 3D example. Yeah.
Yeah, but I mean, you can evaluate it for any complex number, and it's fast. So I don't
Oh
know
yeah.
what's the issue with plotting it. But if you try to plot it in 3D, this is the result. So
So it's like if you just feed it a value, it'll give you out some
yes,
output
yes.
value. It'll be like
Oh, here,
yeah,
right?
right, exactly. Yes, just like that.
No problem. But then if you try to plot it, you get this white square, or if you plot it in 3D, it has the information about absolute value, but I don't know what's going on.
And like I looked into
Oh,
it
that doesn't
online.
evaluate for me for the complex second argument. Or is it like between it can be more than I, right?
Can be what?
Or it doesn't evaluate for me if I try just I as a second argument for 2I. It should be
you
less
need to
than
be
I.
inside the unit circle.
Unit circle. Okay, it's a
Yeah.
unit circle. Okay. Yeah.
And I haven't seen an example of it being plotted. Like I've only seen, looking online, options for just plotting the real or the imaginary part. You can use complex list plot, and you can plot the points, which I've tried to do it in the past. This is like, but there's no way to just do normal complex plot for elliptic theta that I've seen so far. But anyway, we
Okay, so
yeah.
Here's the plot of these eigenvalues for different primes. This is nth prime, and the value. And if you see it goes to 1 billion already. Something's not right. It shouldn't take that long.
Cute. You should have checked whether it evaluates at all for a single argument.
Yes.
Yeah, it evaluates, right?
I don't know. Just try it.
You have to
Have you
try
tried
it.
it?
Yeah, I tried.
What, for the new thing?
I haven't seen you try it.
What?
To evaluate your
the
numeric version of
The
it.
numerical function,
Yeah.
Okay.
But guys, for interest of time, this might be we might have to take this experiment offline.
Yeah. Okay, so let's just.
I see that there's a second Carlos, which I'm guessing means Carlos is now tablet able.
Yeah, I'm ready. I can go.
Okay, cool.
But maybe we can give Richard the way, and then I'll use the last few minutes.
You want to go last?
After Richard, I don't mind.
I think we should just give it over to Carlos. I don't really feel like I don't feel like rushing. Sorry, is something going on? Łukasz is still trying to talk.
No. Okay. So
sorry, I'm just confused. What's
looks
going
like it's try 7.
Yeah, Richard, I wouldn't want you to be rushed either. We can have another one of these.
Yeah. Because I mean, the last time I was restricted to like half an hour or whatever.
Okay, but let's maybe end this presentation. So it evaluates for single arguments. Yeah, I will just run it later. Okay. So.
Łukasz and I have never seen like any actual computations on like the actual eigenvalue. Like we've never seen someone actually apply Hecke operators to these things. So this is like a nice example of a somewhat more intricate aspect of Langlands, which we'll put in the report, where we're seeing things we haven't exactly seen before. And for those of you who saw last week, Łukasz also had a nice visualization of the dells, and so it's taken. There's been a significant learning curve with Langlands, but our conceptual understanding is getting. It's gotten to the point now where I think we're starting to compute things that we really haven't seen in the literature before, and that's what we've been aiming to do. So it's
like, if we looked into it, yeah, we could find the values of like we haven't seen it mostly because of our ignorance, I think, and like non-interest in it. Actually, people just study it theoretically.
Well, yeah,
usually,
yeah,
right.
But it's help. I personally think with pure math, giving concrete examples of things can go a long way. I think it's quite helpful for us, especially, also for other people. Okay. Well, this is the first time we've done one of these roundtables, and one lesson is no one actually likes to be concise. I don't think it's even fun to do that. So there's no way we can have four presentations in an hour unless we like time people. I don't really want to do that. So we should either make these longer, like 2 hours, or we should have maybe a few of them per week, like maybe 2 of them per week or something. But I think okay, that's one lesson learned. So Carlos and Carlos too.
I mean, I feel bad. I mean, should I take the last 10 minutes, or should we split? So Richard can give some update, and I can give some quick. My update is fairly quick. It's just to explain what I'm doing.
I think it's better if you do it. I to be honest, I mean, you saw the thing I posted. It's mostly things that I've discussed already in other meetings. So, yeah, go ahead.
Okay, I'll take the 10 minutes then. Okay, let me see if I can. Okay, so right, so other than working with Nick to keep developing the hypergraph functionality, I am currently, I'm setting my sights on full motif analysis to get to spectral theory,
Right.
and the current. Oh, you can see it fine. Yeah, I just have some faces
Yeah.
onto the thing.
Yeah.
So, the main approach I'm going to take is in the beginning. I think I mentioned in the past. Necessarily has to be a little bit sort of taxonomic, and I have to be a little bit comprehensive within the finite realms that we're gonna go at. So there are two things. So there's taxonomy for hypergraphs, and there's taxonomy for hypergraph rewriting rules. And eventually, we obviously want to think about hypergraph rewriting rules. This is the ultimate goal of our research, because as we know, we can understand most of the formal systems that we're interested in terms of hypergraph rewriting rules. So, but it's important to know that there is, as Nick mentioned earlier today, there is such a huge flexibility. I mean, Nick said this is a more powerful way to do things. I mean, the fact that this hypergraph rewrite rules are so powerful, meaning they are extremely flexible, they can basically do anything. And that's a good thing, because it's proof that this is a very parsimonious system and it's great. But we're actually kind of in the middle of nowhere when we have such a diverse or such a wildly general thing. So the first thing I want to do is to sort of briefly outline the types of hypergraphs that I think are relevant to begin to look at. And these are extremely natural and I'll give one example maybe of each, so everyone has a clear mind of what these things mean. So the first one are the small hypergraphs, and this is very intuitive. So hypergraphs are made of edges, Remember especially for the audience, vertices are kind of this bookkeeping devices. They are kind of the memory in your computer. They're not so much like part of the structure of the hypergraph. It's more where the hypergraph sits, right? So the hypergraph is really made of edges, and Nick has made the point that we have this sort of void edges, and we have the zero edges, the one edges, and so on, right? So
But we also have zero naked vertices too, so they allow to not participate in any edges too. So
Sure. Yeah. I mean, you can point your finger on your sort of memory positions if you want to call them naked vertices for sure. I mean, in the classical definition of a hypergraph, you do have a set of vertices, and you're somehow declaring that this is the memory I'm going to take. But in practice, this is fairly arbitrary, and you know, when actually doing computations, what you care about mostly is the set of edges, and that's why we've implemented these zero edges, and so we have access to all the relevant data at the level of edges, right? So that's the first thing. Things that have increasingly higher number of edges. That's what small means in this context. K-graph means that we simplify so that we are connected, we are simple, so we have sort of the atomic building blocks of hypergraphs. Then there's so maybe I'll give you an example for each of these. So a K-graph is exactly what everyone has in mind as a sort of cartoon of a hypergraph. So, you know, if you have one vertex, maybe you have simply one edge like that. If you have two vertices, you have something like that. If you have three vertices, maybe you have something like this, and then maybe you have another vertex, you have something like that. You know, these are K-graphs, right? I mean, these are simple, connected, and maybe of a definite order. So these are the things to look at and to enumerate and you know, give some signatures and just have in memory. So basically, we need a catalog of these up to some size, and you know, have some systematic way of cataloging.
Okay.
And
Yeah. Okay.
then the other interesting ones are the topological hypergraphs. So topological hypergraphs are hypergraphs that can be thought of as simplicial complexes that are models for some topological spaces. So obvious examples are, so the problem with, so these are kind of two ends of a spectrum, the small hypergraphs, which are the kind of discrete enumerative sort of way of going at classifying hypergraphs. And the topological approach is kind of opposite in the sense that you only look at general topological properties of your hypergraphs. So this is to say, you want to maybe actually classify or enumerate the ones that are literally topological spaces. So things like, you know, if you have something like a chain of two edges, then clearly this is topologically like the interval, right? That's topologically what your space is made of. Similarly, if you have something like a tiling, you know, you have something like this, and you have several sort of ternary edges like this, or remember these are filled. So this is like a disk, right? So let me actually say interval disk, right? So this is kind of the idea, what I mean by a topological hypergraph. So these are hypergraphs that can be thought of as simplicial complexes that are actually topological manifolds or piecewise topological spaces in some general sense. Again, relevant for motif detection because you oftentimes care about the shape of a motif more than the exact motif. Although in the beginning of our investigations, we'll probably actually look at exact motifs, and that's why I would prioritize small hypergraphs and exact shapes other than topological. Then another class that is very natural. I mean, this is almost sort of a, you know, completionist sort of criterion, which is to say, if you have a set of vertices, you can always think for any species of hypergraphs, you can always think of the complete hypergraph, right? So it's the hypergraph that has all the edges on that set of vertices. So I mean, again, very simple. So if you have just one, so that's the one. If you have three, then for a two graph, this is the complete one, etc. Right? So you feel you often want to consider simplicity as a requirement. So you probably want to avoid self edges. So meaning edges that share copies of the same vertex. And the reason being that because we are eventually going to use labeled hypergraphs, we're able to recover this case of repeated vertices with simple hypergraphs. So it's actually enough, in my view, to do all the classification effort with simple hypergraphs, and then use this as skeleton for your actual labeled hypergraphs, which are the ones that are going to be models for all kinds of formal systems, right? And then actually I should say sums and products here. So basically, once we have these, which is, the complete ones are kind of a trivial thing to do. So we have the small ones, we have the topological ones, which are at these sort of two ends of a spectrum. Then we basically take the basic operations of hypergraphs and we say, well, whatever you can make with these, right? That's also part of the classification.
Sure.
So again, just to remember, we'll probably focus on sums more than products, because the product construction depends on what kind of data structure you want to reproduce. And since, we could just do the unordered back product to begin with, which is the sort of parsimonious choice in the beginning. But there are many choices. However, sum, there's basically only one choice, and that's why I would kind of go with sums of existing enumerated hypergraphs. And again, sum is a very natural thing. We've seen it a few times, but just for the benefit of viewers, remember, if you have two hypergraphs, something like this, maybe one here, maybe one here, and if this is labeled like that, then if you sum these two, then this just becomes 1, 2, and then this 3 and 4, right? So you basically just put things together. You add things up. So this is exactly at the level of hypermatrices. This is it's the additive union of hypergraphs, and at the level of hypermatrices, it's just addition of hypermatrices, right? But it's this sort of like co-product addition. Okay, so that's what I'm going to be doing. I'm going to be cataloging these things with the hope to have.
So, by the way, Carlos, so with the taxonomy, it would be great to have a taxonomy. Are we going to make one because no one's done this before, or because we need to do it in our own formalism with our own functionality, or have you just never seen this taxonomy produced before at all?
So the reason why I say taxonomy and not just enumeration, because we need a beginning of complexity, right? So this is actually, I didn't say in the beginning, but I should have mentioned that this is kind of a stepping stone to complexity measures, because
I agree.
A taxonomy with metrics, right? Which is we're as I said, I did say we're going to give signatures to this stuff, right? Like the idea is that you give, you select your however many, like 50, 60, however many small hypergraphs we want to actually put in a table somewhere, and we're going to give them some kind of signatures, right? So these signatures are not going to be based on some efficient enumeration algorithm, as some people have done it before. I think in the physics project there was something like this. There was some kind of efficient enumeration of hypergraphs or rules and something like that. I think the signature should be given based on metrics and based on compositional properties of these things, so that the actual signature is relevant. So eventually, one of the cool things that we could have, which will be very practical for us and for other users, is that in this interactive interface where we draw our hypergraphs, you draw something and it tells you, okay, this is what you drew. This is the signature, this is the thing, right? And I think that's something that's very useful. So anyway, not to go over time too much, but the idea is, once you have this taxonomy, so you have basic signatures for all these hypergraphs, then as Nick showed, hypergraph rewriting rules can be effectively thought of as pairs of hypergraphs. I mean, they're a bit more than that because there's some technicality going on, but essentially you can think of them as pairs of hypergraphs. And so the idea is if you have signatures on sort of left-hand side, right-hand side, then you can start to do taxonomy on the rules themselves in the sense that, so for example, these are some ideas, this is not final of what it's going to look like in the end, but there's quite clear notion of a generative rewrite rule. There's a notion of reductive rewrite rule, like conservative, or a chemical one, right? So just I think I have some pictures here. So a generative could be something like this, right? So you have maybe one single edge, and then it outputs two edges, right? So looking at the basic metric of number of edges, that's something that increases the metric from right-hand side to left-hand side. Something that is reductive is, the classic composition, for example, of morphisms in a category or something like that. That reduces the number of edges. Something that is conservative could be something like a dagger. The classical example of a dagger in a category where basically just reverse the orientation of an edge. If everything is undirected, conservative ones will just basically take some pattern of vertices with edges and will just redistribute those. So something that might look like you have something like this. So you have this, and it gets rewritten to same thing, but somewhere else or something like that, right? That would be a conservative rewrite rule where the number of edges is. I mean, these are extremely elementary examples. I'm just saying that there's some basic metric that you can assign to left-hand side, right-hand side, and that gives you itself sort of taxonomy rules. And then there's the ones that I find quite interesting because we will probably be able to claim that we are recovering theory from people who are doing these higher compositional structures and things that are not just rewrite rules in the traditional sense, in the reductive sense, which are the ones that I call chemical, but these probably require this labeled framework already, because these are rules that check for matching boundaries, right? So in this case, I represent it by having this sort of common boundary between two hypergraphs, and it basically glues the two larger hypergraphs into a bigger one, right? I mean, this is just the example with edges, but you get the idea. And the idea is that you can represent things like tensor products, you can represent things like direct sums, you can represent these very general operations, categorical products and so on, in this way where you basically just put things together and then they kind of chemically react and get this way. So anyway, that's kind of an overview of this at the moment. What I'm going to be doing is going to look at the enumeration, get the sort of zoology as fast as possible, and we can actually start running some quantitative experiments hopefully next week already.
Brilliant. This sounds like a great next step to take. We should schedule some meetings next week and chat about this more.
Sure.
Well, okay, that was very fast paced. I don't know. We can talk about this offline. I thought that was kind of fun. I don't know for other viewers, etc. Like, there are still many lingering questions, like what the heck is a Hecke operator and what exactly are? I mean, it's for me, it's fun, but I'm following all these projects, So okay, there are some things to fix, but that was cool to see, like, us discuss like several things during one meeting and chat with each other about it. Next time, we should give Richard some preponderant time, and Richard, maybe tomorrow we can have a one-on-one meeting and chat further as well. I have to go to another meeting, but and we can improve on these roundtables. But personally, I thought that was really cool.
Yeah, I think it's a good format. I think if we make them 90 minutes, an hour and a half, I think, and everyone gets a sense of pace of how long they can take, like about 20-25 minutes. I think that'll be fine.
Cool. All right, guys. Well, I'll see you later. there are a few. I'll post some things on the Discord tonight about just some logistical things. But yeah, all right.
Sure.
See you
See you
soon.
tomorrow, guys.
All right. Bye bye. See you guys.